Hello, my name is Qurratu Aini Binti Malik. My matrix number is 23304006. I'm from group T3B and my lab partner is Nurul Ilana Binti Muhammad Zaidi. Today I'm going to be presenting my 1GP2 projectile motion Viva. This experiment has four objectives, which is to determine the projectile range as a function of inclination angle, to determine the maximum height of projection as a function of projection angle, to estimate the value of the gravitational acceleration of the Earth, and to determine the maximum projectile range as a function of initial speed. To go through the overview of the experiment, we must know that there are two parts, which is part A and part B. This is the experiment setup. Even though it's not included in the photo, there's also a vertical ruler to measure the vertical height of the steel ball that is launched. For the overview of part A, which concerns gravitational acceleration, the ball is launched at different angles, 25, 35, 45, 55, and 65 degrees, and the range and height of projection are measured. The initial speed is corrected to account for the effects of gravity on the projectile's velocity. Graphs are plotted to analyze the relationship between projection angle, range, and height, leading to an estimate of gravitational acceleration. Both graph of range against squared initial velocity sine squared theta and height against squared initial velocity sine squared theta can be used to determine the gravitational acceleration. For the overview of part B, which concerns maximum range versus initial velocity, the effects of varying initial velocity on the range is examined with the angle fixed at 45 degrees. Data is collected and analyzed with the plotting of graph range against initial velocity to determine the relationship between velocity and range. Moving on to the next section, which is question and answer sections. Question 1. What do you think is the best angle of projection to start the experiment with? In my opinion, the best angle of projection to start the experiment with is 45 degrees, as it typically results in the maximum range for a projectile with a given initial velocity. Starting at 45 degrees simplifies the experiment and provides a solid reference point for subsequent measurements by comparing how the range and height changes with other angles, allowing my lab partner and I to focus on measuring the range and height accurately. Next question. Suggest a way to accurately measure the height of projection of the steel ball in this experiment. An alternative method to measure the height of projection is through video analysis. Set up a camera to record the ball's trajectory from launch to peak height. After the experiment, use video analysis software such as a tracker to track the ball's position frame by frame. The software will provide the y coordinate at the highest point of the ball's flight, giving an accurate measurement of the maximum height. This method offers precise and repeatable results without manual measurement, which can reduce human error. Third question. Suggest a way to determine the time taken for the projectile in this experiment to reach the maximum height. To determine the time taken for the projectile to reach its maximum height, use the video analysis method such as the one in the previous question. Set up a camera to record the entire flight of the projectile. After capturing the motion, use video analysis software such as a tracker to track the position of the ball frame by frame. Identify the frame where the ball reaches its maximum height, which corresponds to the point where the vertical velocity is 0. The timestamp of this frame will provide the exact time taken for the projectile to reach its peak height. This ensures accurate timing by leveraging precise video data. And the last question. No, not the last question, fourth question. From the theoretical physics point of view, will the type of the material affect the range and height of projection? Why and why not? From a theoretical physics perspective, the material of the ball should not affect the range and height of projection if we assume ideal conditions, which means no air resistance. In projectile motion, the range and height are determined by the initial velocity, launch angle, and gravitational acceleration, which are independent of the ball's material. However, in reality, air resistance plays a role, and its effects can vary depending on the ball's mass density. For objects with different density or masses, air resistance affects them directly. A lighter or less dense object will experience greater deceleration from air resistance because the force of air is more significant relative to its weight. Conversely, a heavier or denser object is less affected by air resistance as its greater mass reduces the impact of drag forces. This results in slightly different ranges and heights, but in idealized condition where air resistance can be ignored, the material of the ball does not affect the projectile's motion. And the last question, if your answer to the previous question was yes, state whether steel or wooden ball would give an accurate result and explain your answer. If your answer to the question before was no, explain why in the real experiment performed, there are still significant discrepancies in the range and height of projection obtained using steel and wooden ball. A steel ball will likely give more accurate results. This is because a steel ball is denser, less affected by air resistance, and which in comparison to a wooden ball is more ideal. The reduced effects of air resistance on the steel ball means its motion is more closely follows the ideal projectile motion equation, leading to more consistent and reliable measurements for range and height. Steel, being a denser material, could cause the ball to have a slightly lower velocity due to greater mass, but this would still not change the fundamental projectile motion equation. In this situation, a wooden ball, being less dense, would experience a greater air drag and could introduce more variability in the results. And that is the end of my Viva presentation.